Quadratic problem solving day 2. Today what we're going to use is the calculator, the graphing function of the calculator, to help us determine solutions to quadratic problems. Reading question A, we have a ball that's thrown upward from a height of 6 feet. There's an equation that models this path, which is quadratic. All projectiles launched through the air follow a quadratic path. And so what we're going to do here is we're going to use the calculator to help us solve a series of questions. And the first thing we're going to do is we're going to appropriately graph this situation. So in the calculator, type in the equation that you see into y1. Graphing it on a standard screen makes it difficult to see. You can see where it crosses again, and you can see where it, well, you can see the roots of it very easily. However, the problem now is you don't see the entire shape. So what we need to do is we need to use trial and error to create a window that's going to be appropriate for viewing these problems. Now, from a real-life perspective, we are going to say there cannot be negative numbers. Therefore, the x and y minimums are going to be replaced by 0. Because I could see the parabola come back down and touch the bottom, I do not have to change my x maximum from 10. I could actually reduce it to 5 if I wanted to, but I'll leave it right there at 10. The x scale refers to your scale or interval by which the x-axis is counting. Counting by ones is okay. Again, the minimum for real-life examples is going to be 0. The maximum in this case, you're going to have to use trial and error at first to try to find your answer, but I'm going to put in 150. Additionally, I'm going to change my scale from counting by ones to counting by tens. Graphing that will give me this better picture. And as you can see, I could have reduced it to 5 and gotten it to be a full screen parabola instead. That's what's going to go in this box here. We're going to draw our parabola. So this is going to be 1, 2, 3, 4, and 5, and 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 20, 30, 40, 50. So I'm going to do here is fill in my appropriate viewing window, 10 and 1, 0, 150, and 10. And then what I'm going to do is use my graph and my calculator functions to help me solve these problems. The first thing I need here is I need to determine what that point is. Well, that's the top of the graph. The top of the graph can be found by going into the calculate screen and calculating the top of the graph, which in this case is a maximum, number 4. The calculator is going to ask a series of questions. The series of questions it's going to ask is left boundary, right boundary, guess. Well, left boundary refers to the cursor being placed on the left side of where the top of the graph appears to be. The cursor is on the left side of that, so I will hit enter. Anywhere on the left side will do. The second question it's asking is right boundary. Anywhere on the right side of the top will do. The third is a guess. The guess is unnecessary. So the answer here is 2.49 and 106. You'll learn quickly that this is a quirk of the calculator. The answer to this problem rounds to 2.5 or 2.5. So that is what your solution is for your vertex. So back here, I'm going to go to 1, 2.5, and I'm going to go up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A little bit above 10 or 100 is going to be where this goes. And then I can draw my parabola. Now what I need is I need the accurate location of the place where the parabola touches the x-axis again. Well, the place where a parabola touches the x-axis is known as a root, or a 0, or a solution. So we will be using number 2 to help us calculate that. This time it's asking me for the left boundary, right boundary in the same way. Except now I've got to be on this side of it I'm going to drop below the visible screen. I know that I am below because I got a negative y value, and the guess is unnecessary. And you can see here another quirk of the calculator. That number rounds to 0, so that means I'm at 5.07. Okay, so that means I'm going to come over here and I'm going to do 1, 2, 3, 4, 5, and then 0.07 is about right there. And there is my parabola. From here, what I'm going to do is I'm going to fill in all of my values, or all of my possible solutions here, by using my graph. And because my graph is rough sketch, I'm going to go ahead and use my calculator to help me find all of these. How high is the ball after 1 second? Well, that is going to be x equals 1. So I can use my calculator to help me solve that problem as well. Move this out of the way. X equals 1. So I can go into my calculator here and see this value button. This value means x value. So if I hit enter, you'll notice what comes up. When x equals 1, what is the corresponding y value? That answer is 70. Y equals 70. So you'll see that your calculator is very useful for a lot of functions here that you can solve without doing very much algebra. How many seconds does the ball, after how many seconds is the ball 80 feet high? Well, that means that if I go here, 1, 2, 3, 4, 5, 6, 7, 8, and draw a horizontal line, I'm looking for this and this, because at this point, the ball is 80 feet high. At this point, likewise, the ball is also 80 feet high. Okay? And so what I'm going to do here, very simply, is add in that horizontal line. Upon graphing this line, you can see clearly where that solution is going to be. Trace it, intersect, and enter, enter. Now the only point here about the guess is that we do have to use the guess 2 separate times in order to solve this problem appropriately. The first guess has to be nearer to the first intersection point, and that will give me 1.23. So x is approximately 1.23 seconds. The second intersection point is located here. So I go back and I calculate one more time. And this time I bring the cursor to the second intersection point. This tells my calculator where I want it to calculate, or which one I want it to calculate. And x is approximately 3.77. How long does it take the ball to reach its maximum height? Well, the maximum height was already located for us at 2.5 and 106. So that means it's 2.5. So that would be 2.5 seconds. For how many seconds is the ball in the air? Well, we already calculated that one as well, and that's approximately 5.1 seconds. A reasonable domain and range for this situation will be 0, less than or equal to x, which is less than or equal to 5.1, and 0, which is less than or equal to y, which is less than or equal to 106. Now what we're going to do is we're going to look at this problem slightly differently. Suppose the initial upward velocity of the second ball is half that of the first ball. The initial height is still 6 feet. Our new equation is going to be negative 16x squared plus 40x, which represents the initial velocity, plus 6, which represents the initial height. We're going to use that and compare it to our first equation. So we'll go ahead and activate this one. And I'm going to take my 80 off of the screen so I can just look at my two graphs side by side. Determine a reasonable domain and range and an appropriate viewing window. So you could use this same viewing window if you wish, if you wanted to compare the two to each other, which is, does the second ball go half as high as the first? And you can see that that is not the case. It is actually way less than half of the original height. So that's a good way to view this in a comparison model to answer part C. So we will say no, less than half. And our domain and range is going to be changed slightly, but the way that you find it is no different. So we'll go ahead and do that after we change our viewing window. So that's going to be 0. Remember, real life examples. Let's go ahead and change the Y max to 5. As you can see, 5 was completely appropriate, as well as 50. And our scale for counting on both will still be 1 and 10. Change your window down to 5. And graph. All right. What we're going to do here is we're going to determine the domain and range by finding the maximum and the 0 of this solution. Calculate first of all the maximum. All right. Notice we're on the wrong curve. This is kind of useful if you have more than one curve on a single graph. So I'm going to push the up arrow to switch to the other graph. Now you notice my cursor is there. Left boundary. Remember, we're putting our cursor on the left side of where we think the top is. Bringing it back to the right. Putting our cursor on the right side of where we think the top is. And the guess is 1.24. So that means that the top of our graph is at 1.2431. So the range of our graph is from 0, less than or equal to y, which is less than or equal to 31. Likewise, I need to find this 0 right here, so second trace 0. All right, again, notice that I've gone back to that first curve, push the up arrow, and it switches to your second curve. Again, that's just useful if you have more than one graph on a single screen. Left boundary, drop below. I know it's below because that's a negative. Right boundary, enter. It crosses at 2.64, so that means my domain will end at 2.64, less than or equal to x, which is less than or equal to 0. All right, before moving, oh, sorry, we have another example. I apologize. All right, next. Our second example is going to refer to a situation which is underwater. So you're going to see a slightly different curve, but you still approach it in the same way. All right, so reading through the problem, we gather that we have this equation right here that we're going to use. And I'm going to activate that and deactivate all of the others because it completely changes everything around. And I'm going to graph it. The current viewing window is inadequate for seeing this, so let's go ahead and change it around. I'm going to change it around using 0, 80, 10, negative 6,000, 0, and 100. Now please note, I got all of these numbers through a series of trials and error. I had to view the window and then readjust the window several times before I actually got it correct. So when you do this on your own, you're going to notice that it's not easy to get the correct viewing window on the first try. And in fact, I rarely get the correct viewing window on the first try. So don't be frustrated. Okay, after graphing the situation, you get something that looks like this. Go ahead and draw that in. We're going to find these places the same way we found before. First thing I'm going to do is now find the minimum. The minimum is the bottom of the graph this time. Move your cursor to the left side of where you think the bottom is. Move it back to the right side of where you think the bottom is. And make your guess. 33, so we're going to be about right here. And 5,389, so about right here somewhere. Okay? Parabola drops down. And the last thing I need is I need to know where that 0 is. Remember, the place where it crosses the x-axis is known as a 0. That's why number 2 is what we're looking for here. Go ahead and move this up here. I know it's above because that's a positive number. And there we go. 66. So that puts us roughly right about here. And there is our sketch of our parabola. Okay? How long did it take the sonar to hit the bottom of the ocean? Well, that was 33.2 seconds. We just calculated that in calculating the minimum. How deep was the ocean at that spot? That was 5,389 meters, sorry. And we just calculated that by calculating our minimum. At what time was the sonar wave 4,703 meters below sea level? Again, we're looking at that horizontal line here and here. So what we will do at this point, much like we did in the prior example, is we'll change that 80 to negative 4,703. And we will graph it. Those two places are the places where it does satisfy the situation. So we're going to intersect, enter, enter, and our first guess will be the nearest one here. All right, that gives me at 44.995 seconds. So that is going to be x equals 45.0 seconds. And we will do the exact same thing for the other intersection point. Remember, you've got to move your cursor to the appropriate intersection when there is more than one. And that is going to be x equals 21.3 seconds. Determine a reasonable domain and range for the situation. 0 less than or equal to x, which is less than or equal to 66.3. 0 less than or equal to, let's try that again, smallest numbers first, shall we? Negative 5,389.0 less than or equal to y, less than or equal to 0. Before moving on, please make sure that you solve the third page on your own prior to viewing the video so that you can see how well you understand determining all of these possible solutions by simply using the technology in your calculator. Pause the video now, complete page 3, then check your answers when you are finished. So when an object is thrown vertically upward, this is the formula that you use. This is the explanation for all of these variables. Notice in example number 3, we are going to look at the difference between an object being dropped and an object being thrown, which is example number 4. In object number 3, there is no initial velocity. Or in object in example number 3, there is no initial velocity. Notice your viewing window that can be used. Your numbers may be slightly different. As long as they're close to this, they're acceptable. Most importantly, you're looking for that nice parabola shape inside of your viewing window, where you're able to find all of the missing values, such as maximum or minimum, and of course the places where it crosses the x-axis, roots, solutions, or zeros.